So now we're going to move on to logistic regression. I just love logistic regression. It works really, it's just a really interesting way to study data when you have discrete binary response variables. And we'll talk about that, what that means in a minute. So a logistic regression, it's a type of generalized linear model. If you recall, when Dr. Kate Wilkins gave her talk, she talked a lot about generalized linear models. And everything that we've looked at so far in our class has been a generalized linear model. A linear regression is a generalized linear model. An ANOVA is. And a logistic regression also is, but it's a special kind. It's also called a logit model when the predictor variable is continuous. And so in our circumstances here today, it will be continuous, and I'll show you why. And it's a nonlinear test. You use it when you have a binary response variable, and you can have both continuous or discrete predictor variable. It models what's known as the log odds of an outcome. Don't worry, I will explain what that means in just a minute. It estimates the probability of experiencing one or another outcome. And so you can see in this graph here on the x-axis, we have a predictor variable that is, in this circumstance, it's continuous. And then on the y-axis, we have a binary response variable. So that could be something like male or female. You know, for my purposes, I had a binary response variable of contaminated or not contaminated. And I want to show you here down at the bottom, I've included some links to two really excellent YouTube videos on logistic regression that I highly recommend you watch. Actually, this guy who makes these videos, he's pretty funny too, so I enjoyed them. And as usual, there are a bunch of assumptions, although for logistic regression, there are pretty different assumptions. And so I'm going to go through those now. So a logistic regression is different from a linear regression in that it does not require a linear relationship between a dependent and independent variable. It does not require the error terms to be normally distributed. It does not require equal variance about the mean. It does not require, or the dependent variable in a logistic regression is not measured on an interval or a ratio scale. Okay, so here are the actual assumptions. So we assume that you're looking at the appropriate outcome structure. So that that means that the binary logistical regression requires a dependent variable to be binary. As I said, male or female, yes or no, groundwater contamination, no groundwater contamination. And we're not going to focus on this latter half, but an ordinal logistic regression requires a dependent variable to be ordinal. Don't worry about that at all. Just that first part of what we said about being binary. There's an assumption of observation independence. So logistic regression requires observations to be independent from one another. In other words, the observations should not come from repeat measures or matched data. And there's an assumption of the absence of multi-collinearity, and that means that logistic regression requires there to be little or no multi-collinearity among independent variables. This means that the independent variables should not be too highly correlated with each other. Okay, so we don't really want correlation between our predictor variables. And then there's an assumption of linearity of independent variables, and log odd logistic regression assumes linearity of independent variables and log odds. Yeah, this sounds like a lot, but I'm going to demonstrate what that means in just a second. So although this analysis does not require the dependent and the independent variable to be related linearly, it requires that the independent variables are linearly related to the log odds. And then lastly, there is an assumption of a large sample size. Logistic regression typically requires a large sample size. A general guideline is that you need a minimum of 10 cases with the least frequent outcome for each independent variable in your model. So, you know, you can make that calculation depending on how many explanatory variables you include in your model. So I want to give you a few examples of when you would use a logistic regression to help you understand the different questions that you could ask. So you could try predicting if an individual is male or female based on plumage length. So here we're talking about a species of bird, and perhaps the males have longer plumage than the females. And so, you know, in this example, plumage length is your x-axis predictor variable, and your y response variable is male or female. That's that binary response variable. Another example would be predicting if you will or will not make a basketball through a hoop depending on the distance from the hoop. So here, the x-axis is continuous, and it's the distance away from the hoop. And then the y-axis is made the hoop or did not make the hoop. Predicting if a species will or will not go extinct if global temperatures increase by some different temperature increase scenarios. So here I just gave the scenario of an increase of 0.5, 1, 2, or 5 degrees. And so this is a little bit of a different example, because here we're saying that our x-axis is temperature increase, but these are categories. This is categorical data because we're giving 4 different options for temperature increases. But yet again, we still on the y-axis have that binary response variable, which is will or will not go extinct. And then the last example I give here is predicting presence or absence. So that's a binary response variable of species in a plot based on temperature, which would be a continuous variable, as well as presence of food source in a plot. And that's a dichotomous discrete variable or categorical variable, and the number of water outlets, which is a discrete variable. So what I want you to notice about this one is that for our predictor variables, we've included we've included 4 variables, and they're a combination of continuous and discrete variables. So you can do both. In the example I'm going to show you in just a minute, I'm using a continuous response variable, but you can include all of these different types of scenarios. And so you're going to need to know that for your final, that you can have a continuous a continuous predictor variable, you can have a discrete predictor variable, and you can have a combination of the two. And then for your response variable, it always has to be binary when you're using a logistic regression. Okay, so now we're going to be talking about those terms I had just mentioned, the odds and log odds, and how that relates to probability and why you would do something like this. Okay, so the probability of an event occurring goes along a range of 0 to 1. If something has a probability of 0.5, that means there's a 50% chance of that event occurring. And the odds of that event occurring are the probability of the event happening divided by the probability of the event not happening, okay? So calculating the odds, here you see the equation. So in the example, let's see, we have an example here. So if the probability of an event happening is 0.8, then the odds of the event happening is 0.8 divided by 1 minus 0.8, and that equals 4. So it's the same thing as saying there's 4 in 1 odds. And so I just want to point out this 1 minus the probability of it happening, that equals the probability of an event not happening. So if you have a 0.8 probability of it happening, you have a 0.2 probability of it not happening. And so you can calculate the odds. And one nice thing about calculating the odds is that now it's turned your response variable. It's not just going from 0 to 1 any longer. Now it could go from positive to negative infinity, these odds. And that's important to meet the second to last assumption that we were just looking at for conducting a logistic regression. Okay, but now we're taking it a step further from just calculating the odds. We calculate the log odds. And what this means is that rather than just calculating the odds, you take the log of the odds, okay? So what does that look like? You still take the probability of an event happening, divide that by the probability of the event not happening, and then you log that entire result. So why would you do this? Okay, I want to show you why we would do this here. So let's take a look at the graph on the right. This is the actual data that I have. So on the x-axis, we have the depth to groundwater. And on the y-axis, we have the probability of an event occurring. In this circumstance, we're looking at the probability of there being groundwater contamination, okay? So we're asking, does the depth to the groundwater table, which is a continuous predictor variable, significantly predict the risk or probability for groundwater contamination from a surface produced water spill? So that's what we're asking here. And this is the data that I got from those different spill reports. Okay, so here on the left, this is a spreadsheet of the actual data. And so when we have no and yes, we're talking about the events, and that's this binary response variable. So let's look at that first row. We have a depth of 1. So that means 1 meter below the surface. There were a total of 14 spills at sites that had groundwater 1 meter below the surface. And of those 14 spills, 11 resulted in groundwater contamination and 3 did not result in groundwater contamination. So when you would, So when you would calculate the probability of that event happening at a depth of 1 meter below the surface, we calculate a probability of 0.79. And when we go back and look at our graph on the right, that's what you're seeing plotted here. So that the dot at the very top left, that is representing depths of 1 meter below the ground surface, and about 79% of spills that occurred at sites that had depths of groundwater at 1 meter below the surface. About 79% of those result in groundwater contamination. And when we look at the distribution of data across depths, you see it's clearly not linear. It would require some sort of different equation in order to make that linear so that we could calculate a risk. And that leads us back to log odds. So regressions in general are easier to model when they have when they are linear, and when the response variable can have infinite positive and negative values, like the graph that you see in the middle. That's typically how we want to create a regression. And so if you have curvature to your data, you can transform it so that it is linear. Then you would calculate your parameter estimates and then back transform those to get the linear estimates. So let's take a look at the graph on the left. This is a representation of the type of data that we would have. So let's just say on the x-axis, we have a continuous predictor variable, and on the y-axis, we have our discrete binary variable. And it's this curved function. So what we can next do is take the log odds. And so rather than just taking the odds, which would be the probability of an event occurring over one or over the probability of the event not occurring, because that would keep the curvature to the data, we then log that odd function. And what that does is it transforms our data so that it becomes linear, like you see in that middle graph there. And then that is what we could use to create our parameter estimates. So on the right-hand side, you could see the estimates for a logistic regression, a random logistic regression that was created with some sample data. And so I just want to use this to show you how the estimates go into making your predictive equation. So what this is telling us is that you can see here we have an intercept, and then we have the slope for our predictor variable. So the log odds of our y value, our response variable, equals negative 3.476, that's our intercept, plus 1.825, that's our slope, times x. In the example we're talking about, for depth to groundwater, x would be the depth to groundwater in meters. And in this example, let's just take a look at the p-value. None of those are below an alpha of 0.05. So none of these parameters are statistically significant. So, but going back to the equation that we've generated here, let's assume that it is significant and it is adequately predicting our response variable. These are the log odd coefficients, and they need to be back transformed if you wanted to calculate probabilities. Okay, so now going back to our specific example with the depth to groundwater and the risk for groundwater contamination. Let's look at that data. So we showed here that we were initially looking at the probability for groundwater contamination. And having it graphed this way sort of makes the most sense. You can see just from looking at the data, there seems to be a trend of a lower risk for groundwater contamination with increased depths to groundwater. And so if I take those probabilities though and do just the odds calculation, you would create this graphic. And what you can see here is that we still have curvature to our data. We still see that, you know, the odds for groundwater contamination drop at a quicker rate when you have shallow depths to groundwater than the rate that it drops down when you have more deep levels of groundwater. And then here's the effect when you take the log odds of the probabilities rather than just the odds. And what you can see is now it's actually transformed our data to be more of a linear response, so that you can add a linear regression line to create estimates for your parameters. And so this is really why we take the log odds in logistic regression. It's a two-step process. So we have probabilities that we're able to calculate. We can calculate the odds, which solves the problem of probabilities going from 0 to 1. You know, we're looking for those infinite negative and positive possibilities for our response variable. So taking the odds gives us the infinite numbers that are possible, but then taking the log odds makes our curved line linear. So it's this two-part process that's important for a logistic regression. So now I want to show you some of the statistical results. So I'm not going to expect you to know this R code. Yeah, this is code for R that I've taken directly from my old PhD research. I'm just going to go through it here so you kind of understand what I've done. So what I've said here is that I've named my regression depth.linear.regression. And I'm saying conduct a generalized linear model, as we said that a logistic regression is. And I want you to calculate how the risk for groundwater contamination, or the probability, is affected by varying depths to groundwater. And then I've called this specific data file that I had created. And then I'm saying I want you to conduct a binomial logit. And so in R, they call logistic regression logit. And then the same sort of steps you would need to take as you would for a linear regression. So you would have to ask for the ANOVA, and that would tell you the overall significance of the equation. It would tell you if your predictor variable is adequately and statistically significantly predicting your response variable. So when we look at those results, we see it doesn't give you the estimates or anything like that, the parameter estimates. It just is giving you the probability. And it's highly significant. It's far below an alpha of 0.05. And so we could say that, yes, this logistic regression model is statistically significantly predicting the log odds of the risk for groundwater contamination. Oh, and then the last thing I'll mention here is then I call the summary of the logistic regression. And this is where we'll get the estimate parameters and the intercepts and any other X variables that you've included in your equation. And so here are the results in R that you would get from doing the summary of the logistic regression. You can see first the estimates. So we have the intercept estimate and the depth estimate. And I need to remind you that these are the log odd estimates. These are not the odd estimates. You would need to back transform this in order to get the odds and in order to get the probabilities. Okay, and so I said this, the log odds of the parameter. So when we look at the intercept in particular, it's like saying when the depth to groundwater is 0, the log of the odds for groundwater contamination is 2.3. And for every 1 unit increase in X, in this circumstance, it's an increased meter in groundwater depth, the log of the odds change by this estimate. So in our case, it's saying that the log of the odds decreases by 0.55 for every 1 meter increase in the depth to groundwater. And so when we take those two estimates, we can create an equation. So the log odds for groundwater contamination equals the intercept plus the slope of the depth to groundwater estimate times the groundwater depth in meters. Okay, then one other thing I want to point out here is it provides these Z values. We really haven't talked about this before, but it's pretty cool. It gives the number of standard deviations away from zero on the normal curve. So, you know, when we take a look at these, if you recall, 95% of data on a normal curve would fall within 2 standard deviations. So is this estimate less than or more than 2 standard deviations away from our mean? So we have these really high values, so yes. So that means that I don't have a pointer here to show you, but it means that the value obtained fell within these outlying edges on our standard curve. So that means that we would reject the null and accept the alternative hypothesis that these the intercept and the depth both significantly predict the log odds for groundwater contamination in this example. Yeah, so the last thing I just want to point out here is that you can determine if there's a statistically significant effect by looking at the Z value and by looking at the P value. Okay, so if the Z value is beyond 2, either negative or positive, that means it's a statistically significant effect. Reject the null, accept the alternative hypothesis. There's a statistically significant effect of that parameter. And then you can also tell by the p-value. So if the p-value is lower than our agreed upon alpha of 0.05, which it is both in these circumstances, then similarly, we reject the null, we accept the alternative. There is a statistically significant effect from these parameters on the log odds for groundwater contamination. So there's 3 important things that I'm going to want you to be able to identify from these sorts of summary results. And that's the estimate. You're going to need to know how to turn that into the equation. That's the Z value and understanding that 2 standard deviation cutoff. And then that's the P value and remembering to compare that to our alpha. Okay, so when I conducted that logistic regression, it gave me predicted values. So this is my back transformed probabilities for groundwater contamination based on the depth to groundwater. And that was based off this equation that you see on the top of the graphic here. Like we said, the log odds for groundwater contamination risk are 2.3 plus negative 0.55 times the depth to groundwater. And we had found, as I had showed you the results from the NOVA, a statistically significant equation overall to express this relationship. So there's a major difference at this point comparing this to a linear regression, and that's in a linear regression you would normally calculate an R-squared, and that is based off of the sum of squares, and it would tell you how well your regression line is predicting your data. Well, you can't do the same kind of thing in logistic regression because logistic regression is not utilizing this sum of squares. It does something else, and it's called the maximum likelihood test. And because of that, there's a different sort of calculation to get at the same sorts of ideas of what an R-squared would give you. And it's called a McFadden pseudo R-squared. I'm not going to go into detail about that, but I would like you to think of it just the same as an R-squared. So this is showing you that this logistic regression line is able to adequately predict about 69% of the variability in the data. That's essentially what it means. Okay, but if you recall, I said when you create that the model equation, that's giving you the log odds. It's not giving you the odds, and it's not giving you the probabilities. So what you would need to do is back transform so that you can get those probabilities. So when you have the log odds, recall you have created that linear regression line. And so you need to back transform so then it goes back to your curved line, and it's something that our brains can actually understand when we look at it visually. Okay, so what I'm not going to show you how to derive this equation, but I'm just going to briefly go through it and tell you kind of the important things. So recall that the log odds, if you're looking at the equation on the upper right, the log odds equals the log of the probability of an event happening over the probability of an event not happening. And then the log odds also equals this regression equation. So B plus MX, your standard linear regression equation. And those two things are equivalent. So what do? You make them equal to each other. And you go through actually kind of long derivation process, and you come up with this final equation, which is gives you the value for probability. So the probability of Y, in our case, it's the risk for groundwater contamination, is equal to E to the B plus MX divided by 1 plus E to the B plus MX. You will need to know this equation and be able to use it for your final exam. So recall, here are our parameter estimates that we got in R using the summary code. And so we know that we have an intercept of 2.3-ish and a depth of, and a slope depth of minus 0.54-ish. So now let's plug those values into our equation. So we're saying the probability of groundwater contamination risk equals E to the 2.255 plus minus 0.5451 times X. X is our depth to groundwater in meters. And that whole thing is divided by 1 plus this same exact thing, E to the 2.25 plus minus 0.5451 times X, our depth to groundwater in meters. And so what you could do is you can plug in any value now for X and calculate the probability, or how I refer to it here, the risk for groundwater contamination in this circumstance. So let's do that now. So let's say I'm interested in calculating the probability of groundwater contamination when the depth to groundwater is 3 meters below the surface. So what do we have now? We have our B, we have our intercept, we have our M, we have our slope, and that's from our logistic regression results. We also have X, which is 3 meters. Okay, so we have this equation we just created. Now let's plug in 3 for 3 meters. Okay, so I've taken 3, I multiply that by negative 0.5451. That's negative 1.6353. You can see I did that on both in the denominator and in the numerator. Okay, I've simplified further here. So now we have E to the 0.6197 over 1 plus E to the 0.6197. Simplify further. And what you can see now is you have the probability of an event happening 1.85837 divided by 1 plus 1.85837. Simplify, simplify, and finally we get our resulting probability. And it is 0.65, or a 65% chance of having groundwater contamination at a produced water spill site when your depth to groundwater is 3 meters below the surface. Okay, so when you make a trend line, to express your data, you would do this for every single data point, and then it would get you your trend line. So you would do it for 1 meter, 2 meter, 3 meter, all the way out to as many meters that are in your observed data. Oh yeah, and here I'm just including again what that interpretation is. I will expect you to be able to use this equation. I could either give you a value for X, and then ask you to calculate the probability. I could give you the probability and ask you to give me the value of X. So either way, you would be able to, you would need to know how to do your math, so you can either find the probability or you could find the meters or your X variable. In this case, it's meters below the Earth's surface. Okay, so you would use this equation and calculate probabilities for all of the different depths to groundwater. And this is the trend line that you see here. So as before, we have depth to groundwater on the x-axis and probability for groundwater contamination on the y-axis. You can see all of our observed data and then our regression line. And this regression line, as I said, was created by using the regression model equation that we generated, and then back calculating using that equation I showed in the previous slide to create this regression line. And you can see the regression line really does a great job of predicting the probability for groundwater contamination. It fits the observed data very closely. And now I just want to bring up this question. Is this causation versus or correlation? This is not something we've talked about a whole lot in this class, but I'm going to give you a second just to think about that and come up with your guess, and then I'll let you know. So I hope that you said correlation, because this is a correlation, it is not causation. I did not design this study to be able to ask questions of causation. And usually that's the case with data mining. It's hard to take data that's already been generated and fit it into a mold that would allow you to ask questions related to causation. So really this is correlation. And what is the value of doing something like this? Well, the value is that now we know across Weld County that if you have a certain depth of groundwater at your site, we can fairly adequately predict the risk for groundwater contamination at that site if there was a produced water spill that occurred there. So this could be very important for managers, for landowners considering, you know, putting oil and gas on their farm or something like that. So there really is a lot of value to this. And so now I want to just briefly touch on another aspect of logistic regression, which is that you can have multiple predictor variables in your model. And so if you recall in the beginning, I had mentioned I was interested in, or I hypothesized that larger volumes of water spilled would result in increased risk for groundwater contamination, as well as larger surface areas affected. And I hypothesized that that would also result in increased risk for groundwater contamination. And so here is the layout of how you would write that model in R. And so, you know, last time all we saw was that GW, that stands for groundwater contamination. I had that coded as I think 1 and 2, 1 for contaminated, 2 for not contaminated. And then we're saying, can that be adequately predicted by the depth to groundwater at that site? So that's the question that I had already asked. But here I'm taking it further. I'm saying, can the risk for groundwater contamination be adequately predicted by the depth to groundwater at the spill site, and the volume of water spilled, and the area affected, okay? And in this case, all three of those predictor variables are continuous. But you could, as I had mentioned before, you could also have categorical or discrete data as those predictor variables as well. And so I just want to show you the results from that analysis. And it's kind of interesting. These are just the summary results, so I'm not showing the ANOVA. And we're looking, you can see the parameter estimates. We have that Z value. Remember I said if it's beyond 2 in either direction, then it would be statistically significant. And so, and we're looking at the p-values now. So it's kind of interesting. In this one, it doesn't say that the intercept is statistically significant. And if you recall, in the smaller model with just depth to groundwater being the predictor variable, it did have intercept as statistically significant. And then it doesn't have volume or area showing any statistical significance here. So they are not affecting the risk for groundwater contamination. The only thing that we see in this model that is significant is our depth to groundwater. And so it kind of goes in line with the results I showed just previous to this, that the depth to groundwater does adequately predict the risk for groundwater contamination if there's a produced water spill at that site. But one thing I want to point out here is that because we've added all of these different predictor variables to our model, it gives us less power to be able to distinguish a difference. And so what you can see is that that intercept value here, it is not significant. What the next step I would have done would be to take out of my model the predictor variables that didn't end up actually predicting, because they're just muddying up my model. They are not predicting anything. So you remove them. And that's the standard best practice, that you would remove predictor variables that are not predictive. And once you do that, that gives you that same analysis that I showed right before this, when I only had depth to groundwater as my predictor variable, and groundwater contamination, that binary response variable. And then you do see that both parameters, the intercept and the depth to groundwater, are significant. And that's because you have more power to discern those differences when you have less variables in your overall model. So what I want you to know from this slide here is that all I need you to be able to do is look at those Z values, as I mentioned before, and the P values, and tell me if they are statistically significant, if they have predictive power for predicting the risk for groundwater contamination. And in this circumstance, you could see that only depth to groundwater did. Okay, so to conclude this research, you know, it's kind of funny because I'm focusing on these two different types of analyses, the Mann-Whitney-U test and the logistic regression. And you'll see when you read the paper, there was a whole lot of different things done, a whole lot of different analyses. But I just really wanted to focus in on these, explain to you why I chose those analyses, how they're used, how to do them yourself. And so these conclusions are sort of, they're not just for the presentation I gave, they're sort of for the paper overall. So anyways, we found typically lower median volumes are spilled at sites that have soil contamination. And so that's not anything I showed you right here, but that was with using a Mann-Whitney-U test. So I also looked at soil contamination. Yes, it is contaminated. No, it is not contaminated. And it had that same sort of skew that I showed you before. And so I was able to use that test in a few different ways throughout this analysis. I found that shallower groundwater depths are observed at sites that have groundwater contamination. And yet again, that was with using that Mann-Whitney-U test. So I was able to say, okay, there are more shallow median depths to groundwater at sites that have produced water spills when they are result in contamination and when they don't result in contamination. And then the complementary follow-up analysis I did to that was the logistic regression. So I used that same data and I was able to find out that the depth to groundwater significantly correlates to the probability for groundwater contamination at produced water spill sites, and that you have a lower risk for groundwater contamination when you have deeper depths to groundwater. And so you may ask, well, what are these next steps? You know, you came up with this equation, it's in a publication, did it just go off to die or something? Because sometimes academic literature does do that. Well, no, actually, I realize, so I've taken more of a spatial approach after my PhD. I do kind of some more social research, social environmental research now, and a lot of GIS. And I realized, well, wait, couldn't I model the risk for groundwater contamination across all of Weld County using this logistic regression equation? And the answer is yes. If you know the depth to the water table or the depth to groundwater across a landscape, and it occurred within my study area. So I would be careful about extrapolating these results to areas beyond Weld County because we don't know that they follow these same trends. And that would be something that I would want to study also to see if this same sort of trend is observed throughout Colorado, perhaps. But what I was able to do, and this will be a publication I get out this summer, is that I used ArcGIS to do a process called interpolation. Flat surface that's predicted groundwater depths based on a few different points with known groundwater depths. And so once I had that map that had continuous data for depth to groundwater across all of Weld County, I could use that equation that I generated for my logistic regression and then predict that areas that have high risk for groundwater contamination. And what you can see is that the areas in red, you can't see it very well on the screen, but there's a few clusters of them. There's sort of in the central area, in the southwestern area, and then in the northeastern areas. And this is pretty powerful because maybe you pick a cutoff point and say, hey, if there's a risk of above maybe 5% chance for groundwater contamination, I'm not willing to take it. So you could even find those areas that have risks greater than 5% and a limit and say, you know, you cannot do oil and gas extraction on these locations because they're just too risky. And so that could be a powerful way to protect our groundwater resources while at the same time allowing for oil and gas generation. And so trying to find an approach that that kind of works for everyone. You know, it helps protect these sensitive areas. And so this is where I plan on taking this research next. And you can expect to see a new paper out on this topic if you're interested by the end of summer. That is all I have for you today. And I'm gonna go ahead and stop sharing my screen there. So I just want to reiterate that I'm here for you if you need me. I haven't received many emails from anyone. Grades are all pretty high right now, and most people did well on the midterm. And so that's a good thing. And with how the rest of the semester will go, I think most people are in a good place to do well in this course. And like I said before, if you're having troubles, please get in contact with me, and we can try to work through those. Also, if you are experiencing food insecurity, problems with your internet, technical issues, just any of the crazy situation could be resulting in right now, just let me know, and I'll try to help you get the resources that you need. So with that, I think I'll call it to a close, and take care of yourself, and I hope you all are doing well. Okay, bye.